Hello everyone and welcome to Diana live demonstration. Today we are pleased to introduce early age concrete cracking application in Diana. And during my presentation and demonstration, in order to avoid any background noise, you are muted. And at the end of this session, we're going to have a Q&A session. And you can feel free to raise your question, or if you want to have a real-time communication, then please let me know. I will unmute your microphone. Okay, I'm Yongyan. Maybe I can start our presentation today. We're gonna talk about early age concrete cracking examples. And early age cracking issue of concrete structures are one of the major topic within civil engineering practice these days, and also in research. For example, in this concrete large dam construction and concrete flow and or slab and concrete walls, you can find this early age cracking. Cracking in concrete structures at the construction stage is frequently observed in practice. The main cause of this cracking is inhomogeneous volumetric change of hardening concrete induced by temperature gradient and moisture removal out of the structure. Due to the relatively low heat transfer coefficient of concrete, while the surface layer, for example, are cooling down, the inner part of structure still have high temperature. At the same time, shrinkage may cause decrease in volume of the structure. Also, internal and external restraint take a role of cracking. This is an example of you have increased temperature in early age due to heat of hydration, and the tensile strength will be increased and evolved in time. And in case of 100% restraint or partial restraint, you have different stress. When stress is exceeding excess is higher than developed strength, then there is a possible crack. So today, this is the table of content for today's presentation and demonstration. We're going to talk about what's happening in early age concrete, and then we will explain how to solve it with Diana, and introduction to the demonstration model and different modeling approaches. So this is an overview. There's a concrete column with reinforcement, and there's a steel formwork with support, and this is located probably in looks like a soil. So what's happening in concrete? Hydration heat, and after it will cool down, and depends on this heat, you will get the degree of reaction and also maturity of your concrete. And depends on this maturity, you will get time-dependent properties, for example, Young's modulus, tensile strength, and so on and so forth. And this heat will cause thermal expansion and also creep and shrinkage, which we should consider in general. And the reinforcement, in terms of heat, it doesn't do anything, but because of it bonds with the concrete and it increases the stiffness of structure, it works as internal restraint. And we have formwork. You have, let's say, between 3 to 7 days, depends on your construction schedule. You have a removal of formwork time, and before this removal, heat exchange will be done via this formwork. And after removal, concrete surface will be exposed to the air, and then the direct heat exchange between concrete and the air we can observe. And actually, this formwork works as mechanical support in early age until you remove the formwork. And we can say this works as external restraint. And we have support. Normally we place in the bottom, or if there is a joining structure, or if there is a existing concrete foundation, for example, at the bottom, and that there is a normally connecting reinforcement from this slab to this column, for example, and then it will work as external restraint, of course. So we can observe different cracks in general. We can have two categories. First one is surface crack. Second one is deep and cross-sectional crack. Surface crack occurs due to internal restraint. If you see this picture, you see in heat, along with heat increase internally in concrete, you will get the thermal expansion of concrete, and then you have increased tensile stress around this surface of concrete. And normally you can observe it between 1 to 3 days after casting. And this is mainly due to temperature and moisture gradient, of course. And then when concrete gets cooled down, then normally these minor surface cracks could be closed. So this is one phenomena. And because of this external restraint, normally support at the bottom or existing and adjoining structures around this concrete block, it works as external restraint. And when concrete gets cooled down, and it tries to shrink in terms of volume of the structure, and you will get a higher tensile stress than probably tensile strength in that time. Then you will get cracks. This crack is deep and sometimes it crosses whole section. This is what we want to avoid, because cracking in concrete, it has a very significant effect to durability of concrete. And you can observe this, let's say 10 plus days after casting, and mechanical limitation of strain. Yes, that was the cause of this deep and cross-sectional crack. Now we can talk about how we solve it in DNFA. This is an overview. Our concept is staggered thermal stress analysis, or semi-coupled thermal stress analysis. Firstly, we compute this thermal part, and the result, for example, temperature, degree of reaction, and maturity of concrete, will be used as input in your structural computation. This is a concept, and if I go a little bit further, you have concrete reinforcement and formwork and support. And these heat hydration, cooling, conductivity, heat capacity, degree of reaction, maturity are thermal aspects, while these time-dependent properties, expansion, creep, shrinkage, are mechanical aspects. And in Diana, you can get a crack index if you run a linear analysis. And if you want to go for non-linear, you can use total strength crack-based, our concrete model, and you will get nice cracking, crack propagation, crack width, and crack spacing. And reinforcement, of course, it increases stiffness. This is a mechanical part. And formwork, it has two aspects. Heat will be transferred by conduction and convection and radiation through this formwork. And the formwork works as also mechanical support until you remove it. And we have support. Normally you have heat transfer from your concrete to, let's say, foundation, and then heat will go through this foundation. And also it has mechanical support. It works as mechanical support, of course. This is our concept of finite element modeling. You can consider this aspect. We can start from thermal computation for concrete. We support heat of hydration input in two ways. First one is adiabatic curve, direct input. And the second one is you can directly input your thermal characteristic of your concrete. And the reinforcement normally doesn't do anything. If you want to really consider, let's say, this reinforcement, thermal heat transfer internally in your reinforcement, you can do that, but normally we don't do it. And formwork, heat transfer by convection and radiation, but normally we consider convection only. And depends on your formwork removal time, let's say 3 days, 5 days, or 7 days. You can define different convection coefficient, and then you can model this removal formwork very easily. And support and existing adjoining structures, you can neglect it, or you can model the actual structures or foundation, and then Diana will calculate the conduction automatically. And these time maturity dependent properties, creep shrinkage and cracking, these are you can consider it as aspect of your concrete. And reinforcement, maybe you don't model, or if you want to model, you can take advantage of our embedded reinforcement, embedded bars, grid, and bond slip reinforcement. As far as I know, when we start this, let's say, early age concrete cracking analysis using finite element method, and still in practice, engineers try to reduce the analysis time and modeling time, and they just model plain concrete instead of reinforced concrete, and then they just run the analysis. But these days, modeling of reinforcement is not that difficult. It's very easy. Maybe at the end of my presentation, I can also show you how to do that. And formwork, normally I know that engineers do not model these, but you can consider also fixed support. You can just fix the normal direction of your structure during this formwork period. And after formwork removed, then you can simply deactivate this support. But at the same time, you can consider it as boundary interface, and you can model compression only and no tension boundary. That's also quite realistic, and that's quite easy. And you can actually model your formwork using plate or solid element, and you can assign heat conductivity and capacity in this plate and solid. This is some benchmark test, or if it's very complicated, some in terms of geometry structure, you can try to do this. And actually, I think if you model formwork, it will cause some changes in terms of stress result. But we can talk about it later. We can come back. And support and existing adjoining structures, you can simply model it as fixed support, or you can also assign an interface between your newly casted concrete and existing block. Or if you don't want to model the foundation or adjoining structure, you can simply use boundary interface. We discussed that maturity is very important. Why is it important? Maybe I can share this result. This is evolution of tensile strength in time. If you consider maturity, if you don't consider maturity, then if you don't consider maturity, you will get exactly the same homogeneous concrete property along your section. Let's say it increase, but everywhere in your section is same. But if you consider maturity, then you have a variation of your tensile strength, and you have different the tensile strength is evolved, and then you will see this variation is also changing a little bit. Right. Let me quickly introduce my demonstration model today. I'm going to model simple concrete wall with dimension of 700 in depth and 8,000 in width, and also 2,200 in height. And initial temperature of concrete 20 degrees Celsius, and the external temperature, maybe I can just fix it as 17. And material properties, I'm going to use FIB model code 2010 and class 30, normal hardening, normal weight, conductivity 2.6, capacity this much, and this is with and without formwork, you have different convection coefficient. And during my modeling, I may use different units. So this is just for my information. This is adiabatic curve. I'm going to use this curve in my demonstration. The maximum temperature is 68. It's quite high. The reason why I use this curve is actually to show more cracks in my demonstration. And since I define it in day in terms of my time unit, so I can also bring it to my analysis time step, and later I may have some changes. In overall, this is how I'm going to model. I can show you how quickly you can model this. I'm going to bring this adiabatic curve, and then I'm going to consider these maturity dependent properties, creep shrinkage, and also cracking. I'm not going to model reinforcement now, but later I can show you how to do that. And formwork, I will only consider convection. And in terms of mechanical part, I will not model it. And support, in terms of thermal computation, that means heat exchange. I don't model, and I will just simply fix in X, Y, Z direction. That's very simple. And in terms of output, this is a default, and of course you can change it anytime. We will check temperature, degree of reaction, and maturity. And structural analysis output, I just choose these, but there are plenty more output options you can choose. Depends on your analysis. Crack strength, crack width, and total displacement, and stress, global principle. And I would like to check also Young's modulus and tensile strength in time to see how Diana calculate based on this maturity. And this calculation is actually based on the model code, FIB MC 2010. So I can open my Diana. This is our graphical user interface. Let's say this is concrete wall. I want to go for structure and heat flow and the quadratic mesh. Okay, that's it. This is my concrete wall block, 0.7, and the total width of concrete wall is 8,000 millimeter, 8 meters. I think I can just model symmetry. I can just model half of it because of the symmetry, and maybe then I can reduce the analysis time. So I just enter 4, and height is 2.2. Now it's done. And this is my geometry. If you go here, I have done create, I don't want to modify. And you can follow these orders when you model your concrete block or your structure. I can do mesh seeding in my last step. I will start from property assignment. This is structure solid, and I will choose fit model code concrete, and I will go for cracking. With this option, you can get crack width, crack propagation, and crack spacing. If you turn it off, then you can go for linear, and crack index could be important output, and also creep, shrinkage, young hardening concrete, and also heat flow. So I will go for normal weight, normal hardening C30, and these are just same, and you can see which property we're gonna use. Creep and shrinkage, I can change the unit, Celsius, and okay. So ambient temperature, we discussed that maybe I can assign 17. And this is notional size of member for calculation of shrinkage. I have calculated my block, and there's a 0.6. And then concrete age at end of curing period. In this demonstration, I'd like to remove my formwork at the end of day 5. So I change it to day, and I say 5. Okay, young hardening concrete, this means that time dependent and maturity dependent properties based on model code. And this is important heat flow. Maybe here I choose Newton and second, right. So we discussed that the concrete conductivity of 2.6 and the capacity 2.65. And you can actually have it in time dependent or element age dependent and so on. But here I just leave it. And heat of hydration, we say pre-processing. This is, you can directly input adiabatic heat curve. Here I change my unit to day. And I will copy the table of temperature and paste here. So it's my adiabatic curve. Right, this is done. And then this reinforcement property, in this modeling, I don't model reinforcement, so we can move forward. Connection property assignment. In order to model convection between your concrete and ambient air, we can assign flow boundary. And here we can say convection retro. This is boundary interface, and we're gonna assign it on face. And I models only half of the concrete due to symmetry, so I don't assign any flow boundary here. And element class flow boundary and the material heat flow boundary, okay. And I will use it was with formwork, this lateral part, the side part of concrete, until the end of day 5, it has formwork. And from day 6, formwork will be removed. So I can firstly input the convection coefficient with formwork. It was 14 watt per square meter Celsius. Maybe I can change second. Right, 14. And because of the other input, I change it again. Right. And then you can choose convection, radiation, or both. Here I just select convection. And in order to model the removal of formwork, we can say, we can define this time dependent. So from beginning is until day 5 is same. And from day 6 until 91 days. So this 6,901 kilonewton per meter day Celsius, this represent in other SI unit is 8 watt per square meter Celsius. So we close it and that's done. And assign it. And we model the convection on top of your concrete. Six nine 1.2 from day 0 till 91 is constant. Right, then it's done. So what else do we have? We don't have any external load. Okay, now we attach support. I will just fix all XYZ, and in this phase I can attach symmetry support. This is symmetry in Y direction. So that's done. And here global load, we can input self-weight. Okay. And the attached thermal boundary conditions. In this menu, we can input the external temperature. And when we change it to external temperature, then you can select connections you have defined. I defined convection lateral and top. External temperature will be the same. Here I input only one, and let's see. The reason why I input only one is we're gonna assign a function until day 0 is 15 degree, until 91 days, same, 17, sorry. Actually, your daily temperature in the morning and in the evening is different, and if it's a summer or winter, or it's getting colder or warmer, you have different curve. Here you can introduce those variation of temperature, but in terms of as a sake of simplicity, I just assign 17 until 91 days. Right, and this attach initial field, here we define initial temperature of concrete. We say 20, and that's it. So we have done everything, and then now I can seed. Since we are going to run the analysis until cracking and post-peak behavior, I want to divide in a small element size, quadratic. Okay, looks fine. Then I mesh it. So now we have around 6,000 concrete element, and for this convection, around 2,000 and around 300 for convection on top of your concrete. And materials materials we defined are here, and we can check these boundaries. External temperature or assigned, except this symmetry part, and support, the bottom, and symmetry. And okay, looks everything's defined properly. Now I will set up my analysis. Let's say a concrete wall. Firstly, we can define transient heat analysis. And here, initial condition, we want to consider initial temperature of concrete. And the analysis will be nonlinear. And hydration heat, we just input very small value of degree of reaction in order to trigger the analysis. And calculate equivalent age. This is a very important option that you should consider in order to calculate the equivalent age and maturity. If you don't consider this, then everywhere in your concrete will have the same property. So we calculate this, and some depends on design standard. Some code we can just enter 0, but in MC 2010, if you see the equation, we cannot input 0 because then equation will give the error, an error. So I will enter maybe small value 0.1 day here. And here we enter the step size. I will bring these steps. So this means 0.1 day for 10 times, 0.2 days, 20, and so on and so forth. And I leave the other options as default. And analysis output, I just use the default of Diana. And this is transient heat part. And then now I'm gonna add structure nonlinear. This one is load step. We are not going to use this, so I simply delete it. I need start step, and I need time steps. Why I introduce start step here is in order to model this pouring of concrete or placement of concrete. Here in start step, you can introduce self-weight as additional load. And in this manner, we can introduce self-weight as a start step of the analysis. And I leave it the other options default. And here, time steps, we assign the same time step as transient heat analysis. And because this is a nonlinear cracking, I just want to make sure that we have some more iterations, and then we get the convergency. And in terms of output, I'd like to choose outputs what I want to see. We discussed that I want to see the crack strain, so we go to strain, and we go to crack, add, and then I want to see crack width. We go to stress, and oh, it's in strain, sorry. So here you have crack width in principal stress, and then in stress, I want to see global stress, and also principal stress, and oh, in displacement, I'm also interested in total displacement. Right, and then I'd like to see the Young's modulus in time and tensile strength in time. These are based on, this is not complete, how can I say, the output name, but if you're if you have any question on what's CRK width, this represents crack width. If you search this in our manual, then you can easily find what does it mean. Maybe I can show you how to do that. If you click help, then Dyna manual will be here, and you see you type crack width, and then this explains for crack width and so on and so forth. You have a comprehensive explanation what it is. So I think these are enough for my analysis. So that's done. It took about 20 minutes to complete this model, but because I explained all my steps, but without this explanation, maybe within 5 to 10 minutes, you can finish this one concrete block for early age concrete cracking, thermal cracking. Okay, now I save my model and run the analysis. I'm actually using a laptop, just normal laptop in my presentation. And I was testing if my demonstration model is working fine or not. Actually, I started running analysis like half an hour before, and maybe I can show you that result because we don't need to wait until it runs to the end. So I minimize it, and this is the same model is running the analysis, and it's still step 76. Well, again, we don't need to wait, so I will stop it. And then we can check up to this step in terms of result. So let's check firstly temperature. So this is concrete block, half of the concrete block. And the initial temperature of concrete is 20, and the external temperature is 17. So we increase time step. And then you see this temperature gradient. but we are interested also in core part. You can see clearly the temperature gradient is nicely captured and simulated here. If you are interested in the overview of whole time step, then maybe you can click right click on this temperature result and show table. Maybe I can select this node and top, and I will select time step. Then you can see the temperature gradient is nicely simulated. Maybe you don't want to, you are interested in first 10 days, then let's select up to 10 days. So I think in the bottom, I selected 2 nodes, and top maybe only 1, and you see 3 different temperature graph. And we can also see this degree of reaction. So when is high temperature, then you have higher degree of reaction, and low temperature, low. At the end, let's go to 10 days. I think it will be 1 in whole section. Oh, let me close the other analysis. It's just running, and this is taking many of my computer memory, so which makes the other output displaying slow. Okay, now we have in 10 days after casting, we have almost 1 degree of reaction. That means the reaction of concrete and the hardening is almost finished. And here you can also see the table result. So you have bottom and top. Ooh, I think I selected more. It's fine. Let's go to from beginning till day 10. So degree of reaction is different from depends on your temperature, as well as in time step. Degree of reaction is different in your section. Core part normally has higher degree of reaction, while outer part has less. And equivalent age will be very similar to degree of reaction. So here we plotted day 10 result, but outer part in terms of equivalent age is less than 10 days, while inner part is almost 12 and 13. So what we are interested, this was so far temperature result, and now we jump to structure result. So I will plot the total displacement. Let me change to millimeter Newton. Right. So it was, you can see this part of concrete, lower part is a little bit expanded. And I think this is due to the self weight. And then heat is increasing internally, and then you will see the concrete volumetric expansion. And then upper part is quite big, 0.33. I think until day 3 or 5, it remains like that. Okay. And we are also interested in crack strain, crack width, and so on. I will plot crack width in principal stress. From the beginning, there is no crack. But if I increase time step, still no crack. Oh, yeah. So let's say after 16 hours or 17 hours after your concrete casting, we observe the first surface crack around the bottom of your concrete block. If we increase time step 11, you see cracks are there. And then thermal expansion is done and concrete start cooling down because we fixed the bottom support XYZ. So you see this part, we have stress concentration. And then along with the volumetric shrinkage of this concrete, you have many cracks here. But actually, this is downside of this fast modeling. I neglected this bottom part. Actually, is not fully fixed. Maybe if you introduce boundary interface at the bottom of your concrete, you may get some displacement here in the bottom, and then you will get less stress concentration. Maybe we can go back to other time step, let's say 7 and let's say 8, okay, and then crack strain. Here you see this line. This line represents crack strain, and the crack opening is normal direction of this strain line. And if I increase time steps, you see crack strain is nicely captured. And maybe I can show you also principal stress from time step 2. So I will increase time steps. So here is 17 hours where we firstly observe the surface crack, and this principal stress is reaching to 0.62 megapascal. And the other part here, you can also observe it. If I increase, then you see it's about 1 megapascal in 1 day and 14 hours. Here you see, you can check the minimum and maximum value in this time step. Okay, then I want to see also Young's modulus evolution and tensile strength. Let's check again that in this table and graph. So I will select bottom and then top. Okay, I was successful to choose only 2 nodes. Time step. And then until day 30. So Young's modulus evolution was nicely captured in this manner. And here I'd like to address that we have introduced creep, and Young's modulus evolution will be significantly affected by this creep introduction. Creep works as relaxation in early age of concrete, and if you don't include creep, then you will get higher Young's modulus, and you may get higher stress. And let's change to tensile strength evolution. So our okay is still here, and this is time step. So tensile strength depends on your maturity. You have different tensile strength evolution, and around day 50, 60 is reaching to the same level, but in early days is quite different. Right, so that was a quick demonstration, but we have some more point to discuss. You remember this was my modeling. I just included, how can I say, I didn't introduce reinforcement and I didn't introduce formwork, and I just fixed support and so on and so forth. And then the problem is, because of that limited consideration, I may overestimate the stress, and I may get not very accurate result, which will require more reinforcement in the end, or more concrete in the end, or higher grade concrete. So maybe we can consider some other modeling approaches. What if we model reinforcement interface at the bottom instead of fixed support? Or if we model formwork as mechanical modeling, let's say we attach boundary interface, or we use a plate element, or so on. Or I remove the formwork after day 5, but in case I have formwork until day 7, or maybe you don't want to have formwork such a long day, you want to remove it on day 3. That's also possible easily. And if you model adjoining structures or soil, and then you can also model heat transfer from your newly casted concrete to adjoining structures. For example, here we saw the temperature is same in this from center part and bottom part, the temperature are same. But actually this is not realistic, because depends on what's the bottom, on what's underneath of your structure. Heat will actually transfer to this structure, or in case this could be maybe warmer than your new structure, then heat will go through. So these phenomena can be also modeled. And also, if you have different curing method, or if you insulate your structure, let's say you have water on the surface of concrete for 2 weeks. If it's really massive concrete, and you want to cover your concrete surface in order to prevent too much drying shrinkage, then how we can introduce this? And also different placement scheme of your concrete. Let's say I have a 2.2 height, but instead of one go casting, maybe I can place 1 meter, and then later I can place 1.2, the rest of the concrete. That's a different placement scheme. So those are actually quite important considerations, and these will lead to more accurate result, of course, and actually saving your construction cost, because let's say if you don't overestimate your stress, and then you may reduce the required amount of your reinforcement, and you may also reduce the sectional size and so on. But at the same time, if you model the other aspect, and then that will take some more time and cost. But here, as we discussed, modeling of reinforcement and modeling of interface at the bottom of structure, these two is quite easy. And also formwork modeling and different formwork removal time, you can simply introduce different time table. Here, this is what we have done for modeling of formwork remover, day 5. If you have day 3 or 7, you want to remove formwork, then you can simply change here. And if you have different curing, let's say you have water on top of your concrete or steam curing, then here when you input concrete age at end of curing period, you can change this. And different placement scheme of your concrete, you can simply go for, let's say, construction stage analysis, and you can activate the other part of concrete placement after certain days. It's almost 1 hour, but I think I can show you very quickly how to model these two, reinforcement and interface at the bottom of concrete. Here I'm going to use these properties. Let me go quickly and show you how to do that. I will go back to geometry. Right, this is my initial modeling. And here you can select this face, and then you can extract. Then you will have one sheet. And what I'm going to do is I'm going to firstly model my grid reinforcement. And in order to model it, I just need 2 sheets. And I will duplicate it so I have 2 sheets. And then I will move it to this part of concrete. So the total depth was 700. And then I want to consider the coverage of my grid reinforcement, let's say 40 millimeter. So I will move it to, in X direction, 0.66. And I will select this. Maybe I was wrong in terms of unit. Okay, I will change it to meter, and then okay. Okay, it's here. And then this is a second one. I will move it. So that's done. This is my grid reinforcement, and you just need to assign reinforcement property. So I will select these two. And then you can simply choose material, maybe Gomis's plasticity, and then Young's modulus. I want to have it 200,000 megapascal, and plasticity, no hardening, maybe 500. And since it's grid reinforcement, we need to assign geometry. And it's very simple, diameter and spacing. Maybe as sake of simplicity, I say bar diameter 16, 16, and the spacing 160, done. And that's done. Then this is what we have done for reinforcement modeling. It's quite easy, isn't it? And then we go to connection. What I'm going to do now is I'm going to introduce the bottom interface. So let's say this is bottom interface and boundary interface. This is structure, and you have interface. It's your choice, but depends on your modeling approach. Maybe you can choose column friction or nonlinear elastic friction and so on. Maybe I will choose these in this modeling. And then you have normal stiffness modulus and shear stiffness modulus. Here, let's say I just input 100 times of my concrete Young's modulus. And then here, maybe 10 times, copy and paste. And then cohesion, maybe 0.05. And 30 degrees of friction angle. Then you attach support. This support, XYZ direction fixed, it was attached to my concrete block, but now I introduced bottom interface of my structure. That means support will be attached on the other side of interface, right? So then it's done. So we have discussed that how to do the reinforcement modeling and how to do this interface at the bottom of surface. Now it's done in 3 minutes. And then if you mesh, then in your mesh set, you can check your reinforcement. This is your grid reinforcement. And here, the material of your grid reinforcement and bottom surface. And in this manner, you can consider some more accuracy in your finite element modeling, and then you will get more accurate stress result, and you can optimize your construction. Actually, I also tried this modeling in other computer because my laptop was quite limited in terms of capacity, and I was running this. To be honest, I got some convergence error if I mesh it in the same element size. So I reduced from 100 millimeter to 80 millimeter, and then it was okay. Maybe I can show you okay. So this is your heat result. Even if you model your reinforcement and the boundary interface, it doesn't do anything in heat analysis, but it does its job when structure analysis. So let's say this heat gradient will be the same, even if you don't model it, but the structure analysis will be different. And I think, oh, I didn't get the convergency in step 16. Okay, then that's fine. Then I should find a way to converge it, but let's check. Maybe we can compare until let's say 10 hours. And this is my modeling. I think I closed my previous modeling, but it's fine. Okay, what you're gonna find here is because of the reinforcement and because of this introduction of your boundary interface at the bottom, you will get less stress result, and you will get a more accurate result structure analysis. And then, as we discussed, you can find the optimized way of your modeling and analysis, and then finally, you can reach your target. Okay, it's been quite a long time, more than 1 hour of presentation and demonstration today. And maybe we can start a question and answer. If you have any question, you can open your webinar control panel, and then you can type your question. And or if you'd like to have a real-time discussion with your microphone, please let me know. I will unmute you.